Assalamu alaikum dear students. I hope you're all fine by the grace of Almighty Allah. I welcome you all to the 17th lecture of Thermodynamics 2. Lecture 17. The contents of lecture 17 are entropy change for incompressible substances, entropy change in polytropic process, entropy change in adiabatic process, numerical problems, and conceptual questions and answers. Entropy change for incompressible substances. So, for incompressible substance may include liquid or solid, whereas compressible substances are gases and vapors. So, for incompressible substance, dP for change in pressure is equal to 0 and dV, that is change in volume, is also equal to 0. So in the previous lecture we have derived this relation TdS is equal to du plus P dV. So as for incompressible substance, dP and dV both are equals to 0. So here we have P dV. So change in volume is also equal to 0. So that term, the second term, will cancelled out. So TdS is equal to du. So we have the relation of U, that is the specific internal energy, as CVT. So du, that is change in the specific internal energy, is equal to CVTT. CV multiplied by change temperature. So the relation is TdS is equal to CVTT. We have here inserted the value of du. Dividing T on both hand side, so we have ds is equal to Cv 1 by T dt. Here we have integrated the both hand side with limit 1 to 2, so Cv is constant, so integration 1 by T dt is natural log of T with lower and upper limit of 1 and 2. So when we insert the upper and lower limit, the answer is natural log T2 minus T1. Then we have utilizes the property of natural log, that when two terms are in subtraction, for example natural log a minus natural log b, then we can write natural log a over b. So here we have utilized the property of log. So the final relation is del S is equal to Cv natural log T2 over T1, or change of entropy is equal to Cv natural log T2 over T1. So that is the first relation for the entropy change in incompressible substance. Now we will find another relation to find entropy change in incompressible substance. So here that is also a relation that we have derived in the previous lecture. TdS is equal to dH minus VdP. For incompressible substance, as dP or change in pressure is also equal to 0, therefore the second term of the main equation uh, contains VdP or change in pressure, therefore this term will cancel out. So the formula is reduced to TdS is equal to dH. So H is the specific enthalpy and its relation is CPT. So for change of specific enthalpy, the relation is Cp dt. So here we have inserted the value of change of specific enthalpy, that is TdS is equal to Cp dt. In the next step, we have divided both sides with T temperature. So the relation is ds is equal to Cp 1 over T dt. Then we have integrated both sides with limit 1 to 2. So the final equation is change of entropy is equal to Cp natural log T2 over T1. So as we know that for incompressible substance we have only single value of C. So Cp and Cv are equal. Therefore, the relation to calculate the change of entropy for incompressible substance is C into natural log T2 over T1. So note that the entropy change in compressible substance, that are ideal gases or vapors and other. So entropy change for compressible substance that include ideal gas depends upon pressure, volume and temperature. Because in the previous lecture when we were calculating the entropy change for ideal gas, we have derived three different relations to calculate the change of entropy, which contain temperature and volume in first relation, temperature and pressure in the second, and volume and pressure in the third relation. So the entropy change in compressible substance depends upon pressure, volume and temperature, whereas entropy change for incompressible substance depend upon temperature change only. So here we are discussing a special case for isothermal process and for incompressible substance. So the relation for the change of entropy for incompressible substances, change of entropy is given by del S is equal to mc natural log T2 over T1. Now for isothermal process, the temperatures for both ends or the temperature remain constant. Therefore T2 over T1, they both have T2 is equal to T1 and T2 over T1 is equal to 1. And for natural log 1 that comes out to be 0. Therefore change of entropy is equal to 0. So change of entropy is equal to 0 represent an isentropic process. So previously we have known that reversible adiabatic process is also an isentropic process, but here is a special case that for isothermal process for incompressible substance is also an isentropic process, and this process represent the constant entropy during the process. So you might remember a point in the previous lecture where it says that all reversible adiabatic processes are isentropic process, but all isentropic processes are not reversible adiabatic process. And at that point I have told you that to be an isentropic process, a process need to pass some characteristics that the entropy remain constant during that process. So here is another example for isentropic process, that is the special case, and this is an isothermal process for incompressible substance. So whenever an isothermal process is happening on a liquid or solid, so that is a special case, and during that process the entropy of the system remain constant. So here we have written that previously we know that reversible adiabatic process is an isentropic process. Now we have proved that isothermal process for an incompressible substance is also an isentropic process. So entropy change in polytropic process. So the relation for the entropy change is given by del S is equal to Cv natural log T2 over T1 plus R natural log V2 over V1. Whereas these are the three relations that are used to represent the polytropic process. So the first one is PV power n is equal to constant. Second is TV power n minus 1 is equal to constant. And the third relation is T power n multiply P1 power 1 minus n is equal to constant. We have already derived all these equations in the previous lecture as well. So if you want to find the derivation of these three relation, we have derived these three relation of polytropic process in lecture 3 as well. So when we were revising the course of thermo 1, we have already derived all these form of polytropic process. So now we are considering the first, that is the middle one relation to progress. So we will utilize this relation, that is Tv power n minus 1 is equal to constant, to find the entropy change in the polytropic process. So as that is a constant, so T1 V1 power n minus 1 is equal to T2 V2 power n minus 1. So we will use that relation to find the entropy change in the polytropic process. So in the so the generalized expression for the entropy change contains a ratio V2 over V1. So from polytropic process relation, we will find a ratio of V2 over V1 that comes out to be T1 over T2 power 1 over n minus 1. We will insert the ratio of V2 over V1 relation from polytropic process into the main equation. So we will look what the equation comes out. So the relation for the change of entropy is given by Cv natural log T2 over T1 plus R natural log T1 over T2 power 1 over n minus 1. So here we have replaced the value of V2 over V1 from the relation of polytropic process. So in the next step, we have utilized the property of log, that the power comes out and multiplied at the base side. So for example, we have a x power n. So a natural log x power n. So n will multiply that n that previously was in the power, will multiply with the a on the base side. So here the power is 1 over n minus 1. So here it has multiplied, so r over n minus 1. So the main equation becomes del S is equal to r gamma minus 1. So here we have replaced the value of Cv. So we have two relations. One is Cp minus Cv is equal to R, and the other is Cp over Cv is equal to gamma. We have combined these both relation, and the value of Cv comes out to be R over gamma minus 1. So we have replaced the value of Cv with R over gamma minus 1. Natural log T2 over T1 plus R n minus 1 that was previously in the power, now it has multiplied. So natural log T1 over T2, and the power is 1 now. So in the third step, here we have multiplied it with minus 1 and interchanged the value. So previously that was natural log T1 over T2, now it is natural log T2 over T1. So that's why that minus sign is present over here. In the fourth step, here we have taken the R natural log T2 over T1 term common, so the relation becomes del S is equal to R natural log T2 over T1 bracket 1 over gamma minus 1 minus 1 over n minus 1. So here in the first term we have gamma minus 1, and in the second term we have n minus 1. In the fifth step we have taken LCM of n minus 1 and gamma minus 1. We have simplified the equation, so 1 will cancel out, 1 plus 1 and minus 1 will cancel out, and in the numerator n minus gamma will left, whereas in the denominator n minus 1 and gamma minus 1. So this is the finalized step to calculate the change of entropy in the polytropic process. So here we have replaced the value of V2 over V1 in the main equation. Now we will be using the third equation for polytropic process to derive the entropy chain equation. So the equation is T1 power n P1 power 1 minus n is equal to T2 power n P2 power 1 minus n. So from this relation of polytropic process, we have find out the ratio of T2 over T1. The ratio is T2 over T1 is equal to P1 over P2 power 1 minus n divided by n. So this ratio is calculated from the relation of polytropic process. So in the previous slide that was the third relation. So we have already know how to derive this relation. We have derived that relation in the lecture 3 as well. So del S is equal to R into n minus R over n minus 1 gamma minus 1 natural log. So here previously it was T2 over T1, but now we have replaced it with P1 over P2 power 1 minus n divided by n. So in the third step, we have utilized the property of log, and the power, that is 1 minus n over n. Here we have multiplied it on the back end side of the natural log. So del s is equal to r into n minus gamma divided by n minus 1 into gamma minus 1 multiplied by 1 minus n over n natural log p1 over p2. So here in the previous step we have 1 minus n. So we have taken minus 1 common and the interchange sign of minus in the bracket. So it is n minus gamma into minus 1 n minus 1 natural log p1 over p2 divided by n minus 1 gamma minus 1 into n. So here that n minus 1 and n minus 1 in the numerator and denominator will cancel out, and del s is equal to r into n minus gamma into minus 1 natural log p1 over p2 divided by n into gamma minus 1. So that minus sign we have multiplied inside. So the ratio that previously was natural log p1 over p2 becomes natural log p2 over p1. So here we have another relation to find the entropy change in the polytropic process. So del S is equal to R n minus gamma divided by n into gamma minus 1 natural log P2 over P1. Now we are using the first relation for the polytropic process. So usually that is the most generalized relation for the polytropic process as well. So in the previous step, the term after the natural log was P2 over P1. So from this generalized expression for polytropic process, we are calculating the ratio of P2 over P1. That comes out to be V1 over V2 power natural n. So n is the polytropic index. So that was the main relation we have found in the previous slide. So change of entropy is equal to R into n minus gamma whole divided by n into gamma minus 1 natural log P2 over P1. Here we have inserted the value of P2 over P1, that is V1 over V2 power n, into the relation of change of entropy for polytropic process previously calculated. In the next step, we have used the property of log, so n that was previously in the power multiplied on the back end side of natural log. So change of entropy is equal to R into n minus gamma into n divided by n into gamma minus 1 multiply natural log V1 over V2. So here n is in the numerator and also n is in the denominator as well. So both n will cancel out. So we have a relation del S is equal to R into n minus gamma divided by gamma minus 1 into natural log V1 over V2. So that is the third relation to calculate the entropy change in the polytropic process. So we have three main relation generalized expression for the polytropic process. So utilizing all three relations for representing the polytropic process, we have calculated or derived the relation for entropy change for each of that process. So in one relation we have temperature ratio, in the other relation, second relation, we have temperature ratio, pressure ratio, and the third one we have volume ratio. So here will be using whatever condition is given to us. Sometimes in the numerical problems we will be given the temperature ratio, sometime we will be given pressure ratio, and sometime we will be given specific volume ratio for the polytropic process, and will be asked to calculate the entropy change for that polytropic process. Entropy change in adiabatic process. So as we know that the difference between adiabatic and polytropic process, so a polytropic process is a generalized expression that lie between isothermal and adiabatic process, and all the relation holds for adiabatic process that are derived in the polytropic process as well. But the change is that we have to replace the polytropic index with the adiabatic index. So L is the polytropic index and gamma is the adiabatic index. So here we have the change of entropy for the polytropic process, that is R into n minus gamma divided by gamma minus 1 natural log V1 over V2. Now as we have to replace n with gamma, so both term will be gamma minus gamma. So change of entropy will be 0. Therefore, as we know that the adiabatic process is an isentropic process because the entropy change is 0 during an adiabatic process. So here we have mathematically proved that the adiabatic process, the entropy change during an adiabatic process is 0. So now we will discuss some conceptual question answer as well. Water at 100 degrees centigrade, quality 50% in rigid box is heated up to 110 degrees centigrade. How do the properties pressure, specific volume, so X is quality, U is internal energy, and S is specific entropy change. So here 5 properties are given, and the working substance is water, and the initial temperature is 100 degrees centigrade, and final temperature is 110 degrees centigrade. So quality or dryness fraction is given as 50%. So we know that the value of quality or dryness fraction at saturated liquid line is 0, whereas the value of quality or dryness fraction is 1 at saturated vapor line. So for 50%, we know that that region lies under the dome and it contains 50% of vapor and 50% of saturated. It is a mixture of liquid and vapor, so it contains both 50%. So here is the PV and TS diagram are represented. So as you can see that the at the process 1, the system or the water vapor are in the dome region at quality 50%. Since the box is rigid, therefore V is constant. So for rigid box, V is constant. So P will increase in two-phase region. P is equal to P saturation at given T. So as you know that the temperature rise, so pressure and temperature both will increase. So X will increase. We get close to saturated vapor state. So in the TS diagram, you are seeing that 1 to 2 diagonal line. So as the temperature increase, we will get closer to the saturated vapor line. In the PV diagram, it is a vertical line because here volume remain constant. But on the TS diagram, as the temperature change, the value of entropy also change. So as the box is heated, so energy will enter into the system and it will increase the entropy as well. So as Q is provided into the system or the system is heated, so thermal energy is absorbed by the system. Therefore, U or internal energy, that is a function of temperature. So as Q is absorbed and no work is done, therefore the value of specific internal energy will also increase. So we will revise all these properties that pressure will increase, specific volume will remain constant due to rigid box. X, that is quality or dryness fraction, will increase and the water will move or the system will move toward the saturated vapor. Specific internal energy will increase because heat is supplied to the system and temperature is increased. So as U is the function of temperature and pressure, so therefore Q is supplied and no work is done, therefore specific internal energy will also increase. And as heat is supplied to the system, therefore the entropy will also increase. So another conceptual question answer. Liquid water 20 degree centigrade 100 kilopascal is compressed in piston cylinder without any heat transfer to pressure of 200 kilopascal. So we have given the four properties. So this question is somewhat similar to the previous as well. So here we have a water. Initial temperature of water is given as 20 degrees centigrade. Initial pressure is 100 kilopascal and the piston is compressed. So the pressure is increased and volume is decreased. So pressure is increased up to 200 kilopascal. So the final pressure is 200 kilopascal and no heat is entered into the system. So we are asked to suggest the trend of temperature, specific volume, specific internal energy and specific entropy change. Either they are increased, decreased, or remain constant. So the relation, so as there is no heat transfer between system and surrounding, therefore this is an adiabatic system, and dq is equal to T ds is equal to 0, and incompressible because water is an incompressible fluid, therefore dv is equal to 0, and dw, so change of work is pdv, that is also equal to 0. So because liquid water is an incompressible fluid, so in the current lecture as well we have found out the relation for incompressible substance. So when we were discussing that topic, we have assumed that dp and dv are both equals to 0. So here we have temperature, specific volume, internal energy, and S will all remain same. So for incompressible substance, the temperature, specific volume, internal energy, and S will remain same. Only pressure and enthalpy will increase. So the pressure is increased from 100 to 200, and for liquid or incompressible, H is equal to U plus PV. So as pressure will increase, therefore the enthalpy will also increase. Third conceptual question answer. A substance has heat transfer out. Can you say anything about change in S if the process is reversible and if the process is not reversible or irreversible? So for reversible process, ds is equal to dq by t, that will must be less than 0. So dq will be less than 0. For irreversible process, so change of entropy is the system or entropy transfer plus entropy generation. So ds is equal to dq by t plus ds gen. So as dq is less than 0, but ds gen will be greater than 0. So as we have discussed in the previous lecture as well, the change of entropy, the generation, so entropy is generated due to the irreversibility present in the process. So for reversible process, there will be no generation entropy generated, but for irreversible process there will be entropy transfer plus entropy generation. So we cannot say ds depend on the magnitude of dq by t versus d. So they both are independent terms. So dq by t represent the entropy transfer due to heat or any thermal energy during the process. So let's suppose if the heat is added to the system, then entropy will increase, and if the heat is rejected out of the system, then entropy will decrease. So the term dq by t represent the entropy transfer, whereas the term ds gen represent the entropy generated due to the irreversibility in the process. So the magnitude, what are the magnitude of both that the terms individual, so we cannot say directly about their magnitude. So, but we know that the term dq by t represent the entropy transfer and the term ds gen represent the entropy generated during the process due to irreversibility. A substance is composed adiabatically, so P and T go up. Does that change S? So a substance is compressed adiabatically, so pressure and temperature goes up. Does that change S? So if the process is reversible, then S is constant because ds is equal to dq by t. So if the process is reversible, then reversible adiabatic process is isentropic process. Therefore, S is constant and ds is equal to 0. And if the process is irreversible, then the relation will be ds is equal to dq by t plus ds generation. So the term dq will be 0 due to adiabatic process and ds will be equal to ds generation. So the term entropy generation will be present only due to the irreversibility during the process. Therefore, the S universe will increase. So a reversible process in piston cylinder is shown. So PV and TS diagram for the reversible process is shown. Indicate the storage change U2 minus U1 and transfer W1 to 2 and Q1 to 2 as positive 0 or negative. So for W1 to 2, that is equal to integration P dV, that is greater than 0 because the pressure is increasing, and Q1 to 2 is equal to integration T ds, that is also greater than 0 because the change of entropy is greater than 0. So U2 minus U1, it will be greater than 0 for general shape of constant U curves. Further out, in the ideal gas region, the constant U curve becomes horizontal because for ideal gas, U is the function of temperature only. Numerical problem. So the statement of numerical problem is 1 kilogram of liquid water is heated from 20 to 90 degrees centigrade. Calculate the entropy change assuming constant specific heat and compare the result with that found when using the steam tables. So we have to calculate the change of entropy and compare it with the entropy that is found in the steam table. So as the working fluid is liquid water, so it is incompressible and has only one specific heat value. Therefore, S2 minus S1 is equal to C natural log T2 over T1. So S2 minus S1, that is change of entropy, is equal to C. The value of C is 4.184 natural log T2 over T1. So here we have given temperature are in degree centigrade, so we have converted them into Kelvin. So T2, that is 90 degrees centigrade, becomes 363.2 and 20 degrees centigrade, that is T1, becomes 293.2. So change of entropy is equal to 0.895 kilojoule per kg Kelvin. So now we will compare the result obtained with the results that are found in the steam table. So in the steam table, the portion of liquid water or saturated liquid, we will find the value of entropy for 90 degree centigrade and 20 degree centigrade, that are 1.1925 and 0.02966 respectively. So when we find their difference, that comes out to be 0.8959 kilojoule per kg per Kelvin, and both of the result are very similar up to fourth decimal. So that is your home assignment. So you have to submit the assignment for the entire chapter of entropy as discussed in the lecture as well. So take care. Allah Hafiz.